Welcome to AI Peer Review. Today we're diving deep into, well, a really interesting challenge in multimodal AI. It's all about getting large language models to handle super long videos efficiently. You know how LLMs can chew through huge amounts of text now, like whole books?
Right.
Well, imagine doing that with, say, hours of video movies, surveillance feeds, you name it. It's a whole different ballgame.
Oh, absolutely. It's a massive hurdle. Current MLLMs, the multimodal ones, they really struggle. Efficiency, understanding, both take a hit with long videos. You've got just so much visual data, and a lot of it is redundant, right? It's computationally just very heavy.
Makes sense.
And where really surprising, and this paper points it out, is some models designed for long videos actually do worse than simpler image-based models. It's counterintuitive.
Oh, okay.
So yeah, this paper, VideoChat-Flash, Hierarchical Compression for Long Context Video Modeling, it tries to fix this. Looks at it from all angles, architecture, data, training, even how we evaluate these things.
Okay, so that's our mission today. Let's unpack what VideoChat-Flash is proposing. We need to really dig into how effective their solutions are, what it means for the field, and, what matters for you, our technically minded listener. So let's start with the core idea. VideoChat-Flash. They're aiming for long context video understanding. And the key seems to be this hierarchical video token compression. HICO, they call it.
Yes, HICO. That's really the clever bit. It's a two-stage thing, really focused on cutting down the data without losing the important stuff. First stage is clip-level compression. Happens during encoding, so you break the video into clips.
Right.
A video encoder, one that gets both space and time spatiotemporal attention, processes these clips. Then, and this is neat, there's a similar token merging step. It's parameter-free, so no extra learning needed, super efficient. It basically merges redundant visual bits within the clip.
Okay, merging similar tokens.
Exactly. And the paper claims, get this, a compression ratio of about 1:50.
Wow, 150. Seriously.
Yeah, each frame gets compressed down to just like 16 tokens on average, and they say with almost no performance hit, that's huge for efficiency.
Okay, compressing a frame down to 16 tokens.
Mm-hmm.
That sounds incredibly aggressive. How do they make sure they aren't just, losing the plot entirely? What's stage 2?
Good question. That leads right into the second part. Video level compression. This happens later, during LLM inference. They notice something interesting. In the early layers of the LLM, the attention is kind of spread out, diffuse. But deeper in, it gets much more focused on what matters.
Ah, okay.
So they use that. They call it progressive visual dropout. In the shallow layers, they just uniformly drop some tokens, maybe 50%, something like that.
This is randomly.
Well, uniformly. But then, deeper in, they switch to a text-guided selection. So the text prompt helps guide which visual tokens are most important to keep.
I see. Smarter dropping later on.
Exactly. It boosts efficiency even more. And interestingly, they found it can actually improve performance slightly. Seems it cuts out some irrelevant visual noise, as they put it.
That is clever. Optimizing at both the encoding stage and the inference stage. Okay, so that handles the dense visual input. But even the smartest model needs good data, right? Especially for something this complex. What's the story with their training data?
Right, yeah, data is key. They put together this massive data set called LongVid. It's specifically for instruction tuning on long videos, real-world stuff. We're talking 114,228 long videos and over 3.4 million question-answer pairs associated with them.
That's huge. What kind of videos?
All sorts. Movies, egocentric video, news clips, how-to guides. They pulled it together from existing big data sets like Ego4D, How to 100 Neba, HD Vila, Mira data, so it's diverse. And the QA pairs cover different tasks too. Captioning, finding things in time, temporal grounding, understanding event relationships, scene relationships, even counting events. That breadth is crucial.
Okay, so a smart compression architecture, this anonymous long vid data set. But training on that, it sounds computationally intense, even with the compression. How do they actually train this model?
Yeah, it's definitely complex. They use a pretty structured approach. A multi-stage short-to-long learning scheme builds things up gradually. Stage 1 is video language alignment. Basically, getting the language model aligned with the compressed visual features. They actually freeze the main vision encoder in LLM here, just training the connection pieces using image text and short video text data.
Okay, starting simple.
Right. Then stage 2 is short video pre-training. This builds up the model's core visual understanding using more images and short videos. They often use AI-refined captions here too to get richer descriptions.
Makes sense. Build foundational understanding first.
Exactly. Then stage 3, this is the big one, joint short and long video instruction tuning. Here they mix everything, short videos, long videos, all the different QA tasks from LongVid. They use this duration-based sampling idea. Sample frames more densely for short clips to catch motion, more sparsely for long videos to focus on overall events, sampling between 64 and 512 frames.
Smart. Adapting the sampling rate to the video length.
Mm-hmm. And finally, stage 4 is efficient high-resolution post-fine-tuning. They bump up the visual input resolution from 224 pixels to 448, but they only fine-tune certain parts of the vision encoder, keeping the LLM frozen. More efficient that way.
Okay.
Oh, and one small detail they mention for temporal grounding, finding when something happens, they just use a simple timestamp prompt. Seems it works surprisingly well, better than more complex methods sometimes.
Huh. Sometimes simple is better. Okay, so architecture, data, training. The whole pipeline seems really well thought out, but the proof is in the pudding, right? How do they show this actually works, especially for the long context part? They made a new benchmark, I heard.
They did, and it's pretty necessary. They call it the multi-hop needle in a video A-stack benchmark, or MHNIAH video. It's designed to overcome limitations of the simpler needle in a haystack tests, which sometimes, models could cheat on or didn't require deep reasoning.
Right, like just finding a keyword.
Exactly. This MHNIAH is tougher. They insert a reasoning path multiple images into a long video. The model has to follow text clues step by step to find the right needle image and answer questions about it. And crucially, they include wrong reasoning paths as distractors. So the model really has to follow the logic, not just spot a pattern. It seriously raises the bar for evaluating if a model truly understands and reasons over long video contexts.
Okay, multi-hop reasoning with distractors. That sounds like a proper test. All right, we've got the overview, hierarchical compression, the long vid dataset, that multi-stage training, and this challenging MHNIH benchmark. Now let's put on our peer review hats. Time for the critical analysis. First up, argument and evidence. How strong are their claims? Does the evidence they present really back it up convincingly?
I'd say their claims about balancing efficiency and performance are very strong and really well supported by the evidence. Quantitatively, they bring a lot to the table. On performance, look at their main results table. VideoChat-Flash comes out on top across a bunch of benchmarks. MB-Bench, Long Video Bench, Video MME for both their 2B and 7B parameter models.
And these are standard benchmarks.
Yep, widely used ones. And they're not just inching ahead, they're outperforming much bigger open source models, like that 76 billion parameter intern VL2. Even against proprietary giants like GPT-4o and Gemini 1.5 Pro, they show competitive or better results in many areas.
That's pretty significant.
It really is. And that 99.1% accuracy on the single hop NIAH test over 10,000 frames, that clearly shows its retrieval power is solid. Then there's efficiency. This is where it gets really compelling. The paper shows its compute load is 2 orders of magnitude lower than models like Longvilla.
2 orders.
Yeah, like 100 times less compute. And maybe the most striking thing, it's the only model they tested that could actually finish inferring on 10,000 frames using just a single A180G GPU. Others just ran out of memory.
Okay, that's a very practical demonstration of efficiency.
Absolutely. It directly validates the HICO compression. Plus, their ablation studies are thorough. They systematically test removing different components, HICO, the sampling strategy, timestamp prompts, progressive dropout, and show how each piece contributes. It builds a strong case for their design choices.
Sounds like the core arguments are well defended. Any minor weaknesses or areas where the evidence could be deeper?
Well, it's mostly strong. One tiny point might be the timestamp prompt. They state it gives excellent performance on temporal grounding, and the table shows good results. But a slightly deeper dive into why this simple prompt works so well compared to more complex PIRE methods could have been interesting. But that's a minor point, really.
Got it. Okay, moving on to clarity and structure. How easy is this paper to follow? If someone listening wanted to, say, replicate this or build on it, is it laid out well?
I think it's very well structured, yeah. Very clear. The introduction sets up the problem and their 4-part solution nicely. The method section breaks down HICO, LongVid, and the training stages logically. It's easy to follow their thinking.
And the visuals, do they help?
Definitely. The figures illustrating the architecture, the compression concepts, they're quite helpful. And the tables for results and efficiency are clean, easy to compare. The supplementary material also adds useful details like visualizations for the visual dropout.
Any areas where clarity could be Perhaps slightly improved for our audience.
Maybe just tiny details, like they mentioned using the Qwen 27B LLM, but a few more specifics on exactly how it's integrated or fine-tuned beyond just naming it could be useful for someone really trying to replicate it. Also, they mentioned in the appendix, I think, that another approach, Q-Former, didn't converge well for them. That's a valuable practical insight. Maybe it could have been highlighted a bit more in the main text. But these are small things. Overall, it's a clear paper.
Okay, sounds very clearly presented. Let's dig into the methodology itself. How they did it. Was their approach sound? What are the strengths and maybe limitations of their methods?
The methodology strikes me as really robust and comprehensive. The HICO design, that two-stage compression, is just a very smart way to tackle the specific problem of long video redundancy, especially the similar token merging. Their ablations show it works better than other strategies, even when you push the compression ratio really high.
Right.
The multi-stage training makes a lot of sense too. Starting with basic visual concepts, then scaling up to long videos and complex tasks, it's a logical progression. And using those AI-refined captions is a nice touch for boosting data quality.
And the dataset and benchmark.
Huge strengths. Curating LongVid, that massive diverse data set, is a major contribution in itself. Data is often the bottleneck. And designing the MHNIAH video benchmark, that's a big step forward for evaluation. It really pushes models beyond simple retrieval towards genuine reasoning over long durations, especially with those distractor paths. It makes their evaluation much more convincing.
Okay, those are significant strengths. What about limitations in their methodology?
Well, one thing they mention themselves is that the video level compression, the progressive visual dropout, they only apply it during inference.
Not during training.
Right. They say integrating it with training acceleration techniques like sequence parallelism caused some issues. So the full efficiency gains of that second compression stage aren't realized during the training phase itself. Training might still be quite resource intensive, maybe more so than the inference efficiency suggests.
That's an important practical limitation.
It is. Also, while the ablations are good, they mostly test the presence or absence of components. For something like the progressive visual dropout ratios, they used 50% dropout early on a more fine-grained study exploring different ratios could have given even more insight. But again, that's getting picky. What they did was quite comprehensive.
Understood. So weighing all that, what's the overall contribution and significance here? How does this paper push the field forward?
I think the contributions are substantial, really. Several key things stand out. First, hierarchical compression. HICO. It's a novel, demonstrably effective way to handle long videos efficiently without sacrificing performance. That's a big deal for making these models practical. Second, the LongVid dataset. Addressing the data scarcity for long video instruction tuning is a massive contribution on its own. It'll likely fuel future research.
Definitely valuable for the community.
Third, the multi-stage short-to-long learning strategy. It provides a clear blueprint for how to effectively train models that can handle both short and long videos, bridging that gap. Fourth, the multi-hop NIAH benchmark. Raising the bar on evaluation is critical for progress. This benchmark pushes for deeper reasoning capabilities. And finally, the result of all this, VideoChat-Flash itself. Achieving state-of-the-art performance while being incredibly efficient. Remember, running 10K frames on a single GPU, that's a landmark result. It shows you can have both performance and efficiency.
So the overall significance is pretty high then.
Absolutely. It offers a really integrated solution, architecture, data, training, evaluation, that significantly advances long context video modeling. It demonstrates a viable path towards MLLMs that can handle real-world, lengthy visual data streams effectively.
Okay. Now, a slightly different angle. Potential biases. Did you notice any discernible biases in how the authors presented their work or their viewpoint?
Honestly, the paper seems quite objective. It's very focused on the technical innovations and the empirical results. I didn't pick up on any, political or ideological slant. They're pretty transparent about their methods, the data sets they used, building on existing ones for LongVid, and even the limitations, like the inference-only video level compression.
Right.
Of course, like any research paper, it emphasizes its strengths, but that's just standard scientific communication, not really bias in the problematic sense. They seem fair in acknowledging prior work that influenced them too.
Good to hear. Finally, let's talk about gaps and unanswered questions. What limitations does this work have, or what doors does it open for future research?
Yeah, there are definitely interesting avenues opened up. One we already touched on is training with video level compression. Figuring out how to integrate that progressive visual dropout effectively into the training pipeline, overcoming those compatibility issues they mentioned, could make training significantly cheaper and faster. That's a big potential next step.
Makes sense. What else?
Well, the paper focuses heavily on video understanding, QA, grounding, captioning. Exploring the generative capabilities would be fascinating. Could this efficient, long context processing power be used for tasks like generating long, coherent videos, or maybe complex video editing based on really long, detailed instructions?
Interesting thought. Generative long video.
Another area is robustness. They mention progressive dropout helps with irrelevant visual noise, but a deeper investigation into how robust the model is against different kinds of noise, or even adversarial attacks, especially in these very long, complex videos, would be valuable. And lastly, broader generalization. Longvid is diverse, but testing performance on even more varied, maybe completely uncurated in the wild long videos could reveal new challenges. Also, moving beyond predefined QA tasks towards more open-ended reasoning scenarios.
Lots to explore still. Okay, what an impressive deep dive into VideoChat-Flash. That hierarchical compression, the multi-stage learning, the new benchmark, it really feels like a significant step forward for handling truly long video.
Absolutely. I think the key takeaway really is that balance they found between efficiency and performance. It shows we might not have to make such harsh trade-offs anymore when dealing with these incredibly rich, long, multimodal inputs. It feels like a practical blueprint.
So for you, our listener, maybe the next time you're thinking about what MLMs can do, don't just think about what they see, but how much they can process efficiently. And it does raise that big question, right? As these models get good enough to understand, say, an entire movie or days of surveillance footage, what completely new applications could emerge and what new challenges pop up when we interact with AI that has that kind of deep, continuous context.
Exactly. This paper lays some really important groundwork, but yeah, the journey to truly seamless, long-form, multimodal understanding, it's definitely still unfolding. What stood out most to you from this?
Thanks for joining us for this episode of AI Tier Review. Until next time, keep diving deep.